Welcome back to The Explainer. Okay, today we are going on an absolutely mind-bending journey, and it's all based on the phenomenal research of astrophysicists Fred Adams and Gregory Laughlin. We aren't just looking ahead, a few billion years, no. We are charting out the ultimate far future death of the entire cosmos. It's going to be a wild ride, so let's get right into it. Okay, let's dive into this, because this is, quite literally, the ultimate question. What actually happens when the universe dies? To answer that, we have to travel trillions and quadrillions of years into the future. We're talking about a journey so unimaginably vast that we actually need a literal countdown clock to keep track of it all. Now, you might be wondering how we measure time on this scale. Well, regular years, they are way too small for this explainer. The zeros would literally run right off the screen. Instead, we're using something called ETA, a cosmological decade. It's a logarithmic unit, which means every time ETA ticks up by just one single number, the total age of the universe multiplies by 10. To put that into perspective, today, our nearly 14 billion-year-old universe sits right around ETA 10. So right now, we are living in what Adams and Laughlin call the stelliferous era, or right here at the very start, ETA 10. But by the time we hit ETA 12, the night sky is going to look wildly different. And by ETA 14, the interstellar gas that fuels new stars completely dries up. The whole machinery of conventional stellar evolution just comes to a complete, permanent halt. All right, moving into section 1, the end of stars, the final generation. So here's the crazy thing about the end of stars. Low-mass M-dwarfs, which burn their hydrogen fuel with just incredible efficiency, they're going to outlive our sun by a long shot and become the final burning stars in the cosmos. But eventually, even they fade out. And when stellar evolution ceases entirely, we're left with what you see here, a literal cosmic graveyard called the final mass function. By mass, an overwhelming 88% of all leftover material is locked away in dead white dwarf cores, alongside a scattering of failed brown dwarfs and a tiny, tiny sliver of super-dense neutron stars. With the stars completely dead, we are accelerating forward into the degenerate era. Over the next 10 cosmological decades, the galaxy undergoes a massive, chaotic mechanical breakdown. By ETA 15, close stellar encounters actually fling planets out into the dark. By ETA 19, stars begin evaporating from the galaxy entirely. And by ETA 24, gravitational radiation causes whatever remaining orbits are left to decay completely. Which brings us to section 2, Death of the Galaxy. The dynamical breakdown. Because whole galaxies, they don't just quietly fade away. They physically dismantle themselves through this incredibly slow, violent gravitational dance. First, random near-miss stellar encounters act like a giant cosmic slingshot, ejecting the vast majority of those dead stars straight into intergalactic space. Second, for the unlucky few that remain trapped, gravitational radiation slowly bleeds away their orbital energy. And third, those remaining remnants spiral inward, directly feeding the central supermassive black holes. And the contrast here is just staggering. Today, our Milky Way is a vibrant disk, blazing with the luminosity of 10 billion suns. But if you jump forward to ETA 25, it is completely dead. It's just a freezing, dim collection of remnants. In fact, it's kept barely warm at a chilling 63 Kelvin, only by dead white dwarfs capturing and annihilating dark matter particles. So pushing our timeline even further now, past ETA 30, the macro-scale death of galaxies is basically over. Now, the universe shifts its destructive focus to the microscale, the breakdown of matter itself. From ETA 37 to ETA 40, the very building blocks of the physical world begin to unravel. Moving into section 3, the era of proton decay, where matter erases itself. Now, according to grand unified theories, protons, the fundamental building blocks of all atoms, they are inherently unstable and will slowly decay into radiation. And when this happens, the result is absolutely mind-blowing. Get this. As a massive white dwarf star decays from the inside out, it's going to generate a mere 400 watts of energy. 400 watts. That is barely enough to power a few household light bulbs, just floating out there in the absolute cosmic dark. Adams and Laughlin describe these surreal final moments of stellar evolution just beautifully. As the white dwarf loses mass, it eventually becomes this freezing, transparent chunk of pure hydrogen rock. And as the authors note, at this point, it is simply no longer a star. Stellar evolution is officially entirely over. Which means we finally reach our final timeline update, the black hole era. By ETA 60, regular matter is essentially extinct, leaving a universe populated only by black holes. But guess what? Even they aren't safe. By ETA 83, stellar mass black holes evaporate, And by ETA 100, that is 1 Google years in the future. Even the supermassive galactic black holes vanish completely. Section 4. Evaporation of black holes, the Hawking radiation epoch. You see, thanks to the mechanics of Hawking radiation, even supermassive black holes aren't immortal. Through quantum tunneling, they slowly leak away their mass until they simply radiate into nothingness. And that brings us to what's known as the dark state. This incredibly bleak but mathematically beautiful climax. Once the black holes are gone, all that remains is an infinitely expanding soup of extremely cold diffuse radiation and electrons. The universe reaches its final, formless resting state, drifting forever and ever toward absolute zero. But you've got to wonder, is this truly the end? The research leaves us with one seriously provocative thought. Will this empty, dark universe just expand forever? Or could a massive, large-scale cosmic fluctuation eventually spark a recollapse, like a new big crunch? Looking at this terrifyingly vast timeline really reminds us just how rare, brief, and incredibly special our current era of light and life truly is. So, what do you think? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I will see you next time.